So welcome everyone for another TEPS seminar. We have two speakers today from our trainings, and I will let Professor Regina Lee introduce them.
Thank you. I'm really happy to introduce both of our students. Akash and Peter have been working with me for over a year now, and I think Peter's going to go first. So let me start with very brief introduction of Peter, who is a master's student in our team. He did his undergraduate at Carleton. His research is very much engineering oriented, and I'm really hoping that everybody will see a potential of the technologies that he's developing for future scientific missions that we would like to consider for other advanced space physics. So Peter, floor is all yours.
Thank you for the introduction. I'll just get set up. Can everyone see the presentation okay? Perfect. Okay, so hi everyone. As I've been introduced, my name is Peter from York University, and today's topic of TEPS seminar will be about improving the attitude, determination, and control of small satellites. This will be a bit of a change of pace from the typical TEPS seminar, as instead of focusing on the exoplanetary science, I'll be kind of focusing on the tool that's involved in the science, which are the satellites. So hopefully this will be an interesting topic for everyone. So to quickly go over the agenda, I will talk about the rise of small satellites in recent times. And then I'll be talking about the attitude, determination, and control system of the satellites, which kind of leads into the motivation and objectives. And then the two main topics I'll be discussing today is the improved sun sensor and its impact on attitude determination, and two, the control moment gyroscope and how feasible it is as a potential attitude control option for small satellites. And I will end off the seminar topic with the future work involved on those two topics, as the research is currently ongoing. So there is currently a continually increasing trend of launching small satellites in recent times. A popular recent example would be SpaceX's Starlink, which is using thousands of these small satellites to provide internet at remote locations. The reason why they're becoming so popular is there is a significant cost and time benefit to develop and launch these small satellites relative to larger satellites. This is especially relevant for CubeSats, which are small, really small factor satellites, currently being widely used in demonstration and educational purposes. The reason why they're so popular because they mostly use commercial off-the-shelf components, which lets them use cheaper components and lets them develop faster because you don't need to make any custom-made parts for the satellites. This kind of shows, the graph on the bottom shows kind of the explosive growth in these kind of satellites launch. Starting from 2012, you can kind of see a really big rise in the satellites in operation. And more uses are being found for these small satellites, from Earth observation to broadband communication. So a crucial component in the satellites is the attitude determination and control system, responsible for finding and controlling the satellite orientation. A potential to expand the possible use cases of these small satellites exists by improving the subsystem. So what are some avenues of this, which leads to our current objectives? The first is in terms of attitude determination, we can examine the impact of improving the existing sensors on flight performance. In our research, we specifically look at improving the sun sensor. In terms of attitude control, we look into the feasibility of introducing a new actuator, which is previously implemented on larger satellites into small satellites, called the control moment gyroscope. And to start off, I'll go into the looking into the sun sensor. So small satellites typically use something called a digital sun sensor, which reads in light from the sun onto an array of pixels, leading to an output depending on which pixel is lit up. And as you can see from the graph here, if we zoom into this, we can see at the pixels on the edges, there is a varying level of brightness. Using sub-pixel interpolation, this varying brightness of each pixel can be captured, which leads to improved accuracy. On our research, we want to find exactly what kind of impact this will have on attitude determination. And to do so, we create an orbit propagator and an attitude simulator in MATLAB to test this simulated sun sensor. The vectors generated in the simulation is from mathematical models, such as the Astronomical Almanac and the International Geomagnetic Reference Fields. And from there, we use the resulting sensor output into the attitude determination loop, as you guys can see here. So attitude determination actually involves making use of multiple sensors to estimate the orientation of the satellite. And one never actually really knows the true orientation through just sensors, as it is an overdetermined problem due to readings from multiple different sensors. So there's multiple estimation methods to kind of solve this problem. The most popular and the easiest one is called TRIAD, where it's based on constructing two triads of orthonormal unit vectors using the sensor information we have. Typically, the two sensors involved in this is the sun sensor and the magnetometer. There are other methods of more sophisticated determination, such as the quaternion estimator and the extended Keum filter. Currently in our research, only the TRIAD estimator has been tested, which the results will be shown further down the presentation. So the simulation was set up in a way that there is no eclipse for the duration of the simulation, as if we lose sight of the sun, that kind of defeats the purpose of the simulation. And small control was used to keep the sun sensor face constantly facing the sun. So to quickly discuss some of the results we got, there is an obvious improvement in sun sensor reading with increased subpixel interpolation. The number of bits kind of indicate how much information is carried in each pixel. One bit basically indicates whether the sun sensor is lit or not, 1 or 0. By increasing the bits in each pixel, we can get a more granular reading. Say for 2-bit, it'd be something like it's not lit, it's 50% lit, or it's completely lit, and so on and so forth for increasing number of bits. As we can see, there is a massive improvement from kind of 1 to 2-bit to 4-bit in going from 0.13 attitude error to 0.025 attitude error and so forth. Unfortunately, this does not translate into improved knowledge when using TRIAD. The main reason for this is because the noise level of the magnetometer, which is the second sensor that is being used for the TRIAD algorithm, has a noise level that is significantly higher than the sun sensor. So we found that no matter how much we kind of improve the sun sensor, if the magnetometer noise is too high, then the improvement doesn't really translate into better knowledge of the satellite orientation, as you guys can see from this graph. So this kind of leads into an obvious future work where we test different determination methods. And currently this is being applied for an existing satellite that's currently being developed by University of Manitoba called IRIS. So the improved sun sensor that we were looking into is going to be used on this CubeSat. Their mission is to look at how space conditions affect various geological materials from asteroids and the moon. And they basically require the sun to be hitting all the geological samples that's contained in the satellite. They will be using something called the extended Keum filter to make full use of the improved sun sensor to continually point to the sun throughout its mission life. And to kind of give you a basic high-level explanation, the EKF works by using both the measurements and predictions at different ways to continually improve its output. Unfortunately, I can't really discuss the results because, well, one, it's not my work, so I wouldn't really be able to explain it adequately. And two, they are looking to publish some of the results they were able to get from this analysis, so they asked me not to mention any specific figures or numbers. So to move on to the next topic, which is the CMGs. So small satellites for actuation usually uses something called reaction wheels and magnetokers. They're kind of just spinning wheels, and by changing the velocity of those wheels, it's able to provide torque on those satellites to change its orientation. The control moment gyroscope is an actuator usually used in larger satellites, such as the International Space Station. The benefits to control moment gyroscopes is that it can provide a much higher torque than reaction wheels, and as well, it consumes less power than reaction wheels as well. So obviously, there's a lot of improvement. However, it also, using CMGs increases complexity, and as well, it takes up a lot more space and a lot more mass. So while there's a potential to kind of make those satellites change orientation faster, currently reaction wheels and magnetokers are usually enough to complete all the missions that's being set for small satellites. So one of the questions we really want to answer is, are there any missions that really makes the increased agility through CMGs worth it? So one of the use cases that we have been exploring is the complex coastline observation. So we want to be able to see if those small satellites can be used to kind of look at complex coastlines, such as really jagged coastlines, or even kind of multiple coastlines in one pass. Since those small satellites are usually placed in low Earth orbit, we really need those small satellites to be able to move from one point to another in a very quick rate, because it'll be going over those locations at a very rapid pace. So to do this, 2 complex coastline cases has been set in STK. Quick shout out to the undergraduate student Yan that helped me set this up, as it's a lot harder than it looks to set this up. Coastline and those small satellites should be able to sweep through this coastline in a short amount of time. So the 2 coastlines that are in focus is one coastline E, which is Prince Edward Island, and it will sweep through each of this point, having about a second of pause at each point. So the total time it takes to sweep is about 38 seconds. The second coastline is coastline F, where it sweeps through a partial coastline of Newfoundland and Labrador, and we chose a especially jagged coastline just so it requires a lot of change in direction to sweep this coastline properly. From there, we get the ideal torque profile to be able to sweep this coast, which is basically the torque that's required to perfectly follow through each point. And for small satellites, the most common configuration is using 4 single gimbal CMGs in a pyramid setup. This reduces mechanical complexity, and we are able to fit this in a smaller volume than some of the other configuration. And as a quick explanation of how CMG works, it's basically a flywheel that's on a gimbal, and by rotating that gimbal as the flywheel is continually rotating, it provides torque. And the special thing to note about this is that the direction of the angular momentum will change as it's on the gimbal. So this kind of highlights some of the complexity of CMGs. We need multiple CMGs to be able to provide to cover all the required direction of the angular momentum. And 2, we need to be careful of something called a singularity, where, a certain orientation of the CMG, we lose control over a certain axis, kind of like a gimbal lock. So we built this simulator in Simulink, and if we really want to cover this in detail, this could easily take up a time for another seminar, so we'll be covering it in high level. It's the similar setup to the sun sensor simulator, but with more focus on the control and actuator components. We provide a steering law called the pseudo-inverse steering law, which is a relatively simple steering law to avoid any singularity. The STK results are used as the sensors to kind of dictate, hey, satellite, this is kind of the torque you should be generating, as the STK results are the ideal torque. We set the maximum torque that can be generated by each CMG as 200 million newton meters, and the CMG parameters are based on MSCI's CMG that is currently in development. So to get into some of the results that we've seen so far, we can see in the top left graph, it is able to follow the desired torque really well. But once you zoom in a bit, there is some differences. And the problem with these differences is that this causes a drift in pointing error, as the satellite is not explicitly controlled according to the torque error. So as you can see, the pointing error kind of rises linearly. This is because once there is an error that kind of continues on forth and stacks up over time. And as such, the torque errors kind of end up adding up slowly, and any drift in point is not stopped. This is made even more explicitly in the more complicated case of the Newfoundland Labrador. As we can see, once there is an error, it rises up very quickly. And in this case, we also find an interesting scenario where it is unable to hit the desired torque profile, as the desired torque profile is kind of curved in certain regions, but the actual output ended up being straight. So this is kind of left to as future work to investigate why this is happening. So to quickly go through some of the future work involved, for the sun sensor, we really want to investigate thoroughly some of the other attitude determination options, see what kind of improvements we can get with the improved sun sensor, and whether we can really take advantage of it. For the CMG feasibility study, we want to, fine-tune some of the coastline missions, kind of see some of the variations we can make through the missions, and what kind of results we can get from that. 2, apply control to reduce the error in the torque profile. And 3, it was made implicit that what we are doing with the CMG cannot be done with the previous actuator because of the high torque required. But we also still want to directly compare against other actuators just to kind of see how much better the CMGs will be. So kind of to wrap this around in the context of TEPS, the improvements in the small satellite system can result in the availability of cheaper and faster missions, which hopefully will help open up space for more common purposes as well. So that is the end of my seminar, and I'll be happy to take any questions now.
All right, thank you, Peter. So we have time for questions. Stefan?
Yeah, hi. Thanks, Peter. There's some more about CubeSats in general, but one of your first slides, there was like the number of satellites, including failed launches. And I noticed that the success rate for launching CubeSats is like 90-something%, but that still seems like a relatively low success rate. Like if 1 out of 11 or 12 fails, is that kind of a byproduct of it them being cheap, or?
It's less of a byproduct of it being cheap and more of a kind of, it's being used more and more to kind of introduce universities to kind of the whole developing a satellite and the launch process. So instead of kind of like kind of professional environments developing satellites, and we kind of use it as an educational purpose for universities and kind of students to get a hands-on experience on kind of developing a satellite from scratch. So I think it's kind of a byproduct of that more than kind of using cheaper components, as since there's less budget involved, I would say, in these small satellite development in terms of kind of like personnel and things. I think that kind of has an impact on its development.
Okay, and just a quick follow-up, is it the failed launch, is it that it doesn't kind of reach the right orbit, or is it once it reaches the orbit, it just kind of doesn't work for some reason?
From personal experience, I think it reaches the orbit because the launch vehicles are able to kind of put it in the orbit. But there's a lot of kind of errors once it is in orbit. And the CubeSats are considered a secondary payload. So it has less priority than the primary payloads in reaching the orbits correctly. So there's also that case.
Okay, cool, thanks.
Any other questions? If not, let's thank Peter, and we can move on to the next speaker, who will be introduced by Professor Regina Lee again.
Thank you. Thanks, Peter. I am again very excited to introduce Akash. He's a PhD candidate in our group. Unlike Peter and many of us, Akash actually has a physics background, also from York University in undergraduate. He's been lately working with Honeywell in collaboration with a number of other universities in developing a very exciting technology called OPA. But his thesis overall focuses on microphotonics, which goes well beyond just an OPA design. And today he'll probably walk through various steps in developing this new technology. And in listening to his discussion, and I want everybody to think about how we can use it again in our future missions, because we really believe that photonics is one way that we can improve capabilities of small spacecraft and achieve a lot more than what we are doing today, and maybe even prevent some of these failures that we talked about earlier that Peter discussed in CubeSat design and whatnot. So Akash?
Hello. Can you guys see the PowerPoint?
We do.
Okay. So thank you for the introduction. So today I'll be talking a bit about microphotonics, but I will specifically focus on the optical phased array as well, because that has been what I've been focusing on in the recent times. So again, my name is Akash, and the names that you see down here in the presentation, they're actually fabricated on the chip that we've made. I had a chance to put all our names on there. So then I think this is the smallest that our names have ever been written in humanity. So, which was pretty cool. So this is about 35 microns tall. But to get into what we're going to be talking about, I'll start off with microphotonics. So give you an idea of what it is, some of the history behind it, talk about some applications, and then also give you some examples of microphotonic components. So you start to get some intuition about what you can do with this type of technology. And then I'll talk directly about the optical phased array. So I'll give you an introduction, but then also talk about the proposed design that I've been working on with Honeywell in terms of the required components that we've been able to develop with some industry and academic partners. Talk about the layout, the packaging, and then also talk about some fabrication results. So once we actually meet this device, what do we see and what does it look like? Also, because these devices are very small, you have to pay a lot of careful attention to how you go ahead and test them in terms of the hardware and software. So I'll talk a bit about that as well. And then finally, we'll cap off with some preliminary results that we've been seeing with the phased array. And then I'll just recap and bring everything back together. So an introduction to microphotonics. I think it's better to talk about the specific material that we're using, namely silicon microphotonics, because there has been an explosion in the applicability of that in recent years. So, but the definition that I'll show you in the next slide really does apply to everything else. So silicon photonics or microphotonics studies the generation, the transmission, modulation, processing, and detection of light using silicon as the optical medium. Now, this is a very vague definition, and I specifically left it very vague because you have to remember that this is a technology platform which a lot of different things can be done with. So for example, when I say generation, I'm talking about lasers, LEDs, transmission, so everything from these micron-sized waveguides that I'm using to fiber optic cables, part of our telecommunications networks, or in our Rolls-Royce. Modulation, being able to change the phase, the amplitude, the wavelength of your light is very important. Processing, so giving some input and output, you can use an optical circuit to accomplish that. Detection of light, so photodetector, a CCD, for example. And again, it's important to stress that this definition goes well past just silicons because you can use a lot of different types of 3-5 semiconductors. 3-5 representing the groups on the periodic table, 3 and 5. Another example of material would be lithium niobate, for example. It really depends on the application that you care about and also really the resources and budget that you have as well. So some relevant history to the field, again, specific to silicon photonics. There was some early work done on passive waveguides and active waveguide-based devices such as switches and modulators in about the mid-1980s. Why is this important? Well, switches and modulators are very important in our telecommunications history. And because of their importance, a lot of industry and governments have kind of realized that we needed to mature this technology. So around 2004, a lot of money kind of flowed into this space. And again, this was primarily because of its connection to telecommunications, the ability to encode data within a beam of light that can be sent from location A to B very fast was very important to a lot of different industries. But also the really big reason why silicon took off and why not a lot of other materials is because of strong connection to CMOS fabrication techniques. Like when you're thinking of why a specific technology takes off, you have to think about how does it leverage the existing resources that are actually available to it. And the ability to leverage existing foundries that have been used for PCB production for silicon photonics has been a key driving factor in making sure that this has come out above other materials. And now silicon photonics is applied everywhere. And what do I mean by everywhere? And if you're interested, there's this very nice paper by Dr. Ye from Carleton that talks about some of these advances and history as well. So when I say applications, I mean telecommunications, right? The fiber optic network that we have globally, the lasers, self-explanatory, quantum computing. There's new companies that have very exciting ideas, such as Zandu, that are trying to create photonic circuits specifically for quantum computing. Remote sensing, right? We had a graduate student that was looking at creating a thermal planar waveguide for a transform spectrometer for methane detection. Inertial sensing, which is the other half of my thesis that I have neglected for a while now, essentially making an interferometric fiber optic gyroscope, like an inertial sensing based off of an optical sensor. the seismic effect specifically. Biophotonics, right? Basically kind of taking all of these complex chemistry and biology toolkits and putting them on a chip that can fit literally on your pinky. But okay, this is great and all, but how do you actually go about making these systems? Well, the idea is very similar to PCB production. You have to first make your optical components and then route them together in some way to make an optical circuit, right? Which you are all aware of. And the idea really comes from like traditional optics, where you have your benchtop set up, you have your different lenses and everything, and then you have a laser that points through them. So the first thing you need are waveguides, the ability to route light from point A to point B, from one component to another component, right? And there are different types of waveguides. There's buried waveguides, diffuse waveguides, each with their own specific purpose and use case. We are specifically using a buried waveguide due to simplicity, its applicability for high power use as well. How do you go about actually making these? Well, there's a lot of different tools that you can use. For example, you can propagate Maxwell's equations on a finite spatial and temporal grid. And you can actually go ahead and see how this light propagates through different effective indexes, profiles. So you can do things like look at the optical loss, or as in this simulation, look at how light actually couples from one waveguide to another waveguide if they're some separation apart. If you only had the ability to go in a straight line, that wouldn't be very interesting. So having the ability to bend your light is also a key factor. And again, you can use something like an FDTD simulation to simulate how the light would propagate and how the light would be lost due to scattering losses, for example. You also need the ability to split your light and combine your light. For example, if you're making an interferometer, you need to think about how you are going to represent your beam splitters. So for example, you can use a Y branch or these cool multi-mode interference devices. And then finally, you need some way of getting light into and out of your chip, because again, these chips can get very small. When you see a butterfly package in your optical components inside, there's usually going to be a photonic device in there that is coupled to some type of fiber that you interact with. So you need to think about your input and output. Two common ways, for example, include the edge coupler. And as the name suggests, you basically take a waveguide, you taper it down or up such that the optical mode at the edge of the waveguide is going to match the optical mode of your fiber. And you do this because the optical mode of your waveguide is going to be very small relative to the size of the optical mode coming out of the optical fiber. And then you can also apply something called a grating coupler, which basically uses diffraction gratings to go ahead and change the propagation direction of the light as well through diffraction. Another thing that you might want to think about is, okay, I said modulators initially, right? How can you actually go ahead and create these modulators? So for example, you can actually change the refractive index of the material, and you can change the propagation constant of the light. And you can change how the light is going to propagate through your waveguide. For example, you can use something called the thermal optic effect, which is what we're using, where you essentially just have your optical waveguide and let's say a heater on top, and you use the heater to heat up the surrounding areas. And that change in temperature is going to cause a change in the refractive index, and therefore the effective mode of the light that's propagating through it, changing how fast it's going through, the light is going through it. You can also apply an electric field and change your refractive index that way, right, through the electro-optic effect. So with all these components in mind, you can start to think about how we can kind of put them together to make an optical phased array. And coincidentally, all the components we talked about are all the components we've been using for the optical phased array. But before I get into how the components translate into a layout, we'll take a stop and we'll talk about what optical phased arrays are and why we really even care about them in the first place. So recently, there's an increased interest in optical communication in space to help alleviate the need for different communication bands. And this is because there's a high number of satellites that are recently being launched, as Peter had pointed out. So people are looking for different communication bands that are also allowing for high data throughput. So people look at higher frequencies, but another idea is to apply optical communication as well. So if you imagine it, you basically have two satellites that are essentially trying to point a laser, and you're trying to point a laser from one satellite to another satellite. And in this beam of light, you've encoded data through, for example, let's say intensity pulses, right? Where if you see the light, it's a 1, and if you don't, it's a 0. this is great, but a key part of this is the pointing. You need to be able to point several thousand kilometers away very precisely. And if you don't, it doesn't matter if you've encoded the data in there, if it never reaches there, there's no point to it. So a big key aspect to this is actually the beam steering solution. People usually just introduce a mechanical beam steering solution. So if you imagine just a stage which can tip and tilt. But the fact that it has moving parts makes it unreliable in space terms. And if you can find a solid state solution to it, it's much better. An optical phased array is that solid state solution. And so that's what we're exploring. So again, we want to use OPAs for beam steering and formation. And this GIF is kind of nice in the sense that it kind of shows you everything that, it shows you the theory behind it. So what you do is that you control the phase of several discrete emitters in such a way that the cumulative wavefront that you can see like over here is steered in a specific way. And now this can be one dimension or two dimensional. And you can actually go ahead and form several patterns with a two-dimensional beam steering, essentially by rastering the beam across some type of plane at a given frequency. And in this GIF, you can actually see the different components that make up an optical phased array. So you need something that actually generates your signal. And then you have some type of splitter device that actually takes, let's say, one input and converts it into n outputs. You have a phase shifting element, and then you have an antenna, right? Everything that we just talked about, where in this case, our antenna is going to be our grading couplers. So what are some common applications? So in the beam steering world, we have optical communication for the transceiver and receiver side. We have remote sensing, right? Being able to properly and accurately probe a section of space is very important. And in that same respect, LiDAR, being able to raster an optical beam across some topology is actually very important. So what do we want to do specifically? We want to do optical communication between satellites and possibly even apply for other terrestrial applications. So we want to replace the mechanical beam steering solution with an OPA, mostly because of its size, cost, and lack of moving parts. I didn't mention, but the way you make these devices is that you make a bunch of them at a time in some type of a wafer situation, which actually cuts down the actual production cost of this as well, right? But it's sometimes even $20,000, $30,000 per unit. And if you're making these multi-satellite constellations, that adds up very quick. So is what we're doing novel, right? Yes and no. Everything has been done in specific segments. So what we want to do is a 2D beam steering. Well, people have done that on chip. The novel aperture that we're using is a multi-circular aperture. So if you think of the gratings being oriented in such a way that it's a dual ring concentric ring, dual concentric rings, yeah. But people have done that before. And we want to have a lot of emitters. Well, people have made large-scale arrays as well, but it's the intersection of these 3 points which really makes our application quite novel and hard, because when you're working with a large-scale nanophotonic array, the parameter spaces for optimization and phasing up, for example, becomes very large. So what is the proposed design? We want to essentially make a 100 emitter dual ring structure, right? And you can see the 2 rings here. And again, this is the visual image of the fabricated structure that we've made. And I believe the diameter of the outer ring is about 5 millimeters to get an idea of scale. We want to be able to handle 10 gigabytes per second data rates, and we want about 2 watts of optical power. The data rate is more of a function of the actual modulator used to encode the data and not really the OPA. But the 2 watts is important for the OPA because you need to make sure that if you require 2 watts to go X amount of like several thousand kilometers away, then your entire optical circuit needs to be able to handle 2 watts of optical power. So to make our entire design, we talked about components already, but to list them off, we need waveguides, we need splitters to split the light to get the 100 channels that we want. We need grading couplers for emitters, thermal phase shifters, because that is what our material supports, edge couplers to couple light into the chip, bends to be able to create an efficient route. And then since we have thermal phase shifters, we also need an electrical interface. So we have 100 thermal phase shifters, but these thermal phase shifters are basically just really bad wires, right? They're essentially just little wires that heat up when you pass current through them, but you need to feed current through them. So you need an electrical interface. So once you have all the components, the next part is actually making a layout. And the process is very similar to how you would make a PCB layout, in the sense that you would make some type of schematic, send it to the foundry, and then they would make it. So the main layout that we care about here is what I'm pointing out with my mouse. Hopefully you can see it, where we have this one input being converted into 100 channels through this MMI tree. And then each of those channels goes through a phase shifter where we adjust the phase of it. And then after the phase is adjusted accordingly, the light is then routed to your actual emitter, and then the light will be emitted towards you out of the plane of the computer. Now, to make an efficient layout and really go through an efficient design process, you really need to test all the individual components that you've made as well, especially if they haven't been made before. So everything you see around and all these other different structures are actually just test structures, testing the parameter space used for each of the test structures. It helps validate the actual design process that you've chosen, but also gives you confidence in round 2 if you need to make slight changes to various components. And to really get an idea of scale, I think it's important to note that the entire layout, this entire square, is about 18.2 millimeters by 18.2 millimeters, which is smaller than a penny. So once you give it to the foundry, they need to fabricate it, right? And so what they do is they do fabrication done through standard photolithographic techniques on the silicon nitride waveguide platform. And what this is essentially, the picture shows the different layers that we've been using. So we have the waveguide layer, we have the little etches to create the diffraction gratings, we have these other amorphous silicon gratings, and then we have aluminum that represents the actual phase shifter, heater, and also how we interface with the heater on another layer. So once you make them, you can take some nice visual images of them. So the first image is an MMI tree, where it goes from 1 input to 100 outputs. Then you have your grading arrays that I showed you before. And then these are the way we actually do the electrical interface. So you create these bond pads on the photonic chip, which are essentially these square aluminum pads. And then you basically just bond a wire to one of the bond pads on the photonic chip, and then the other end to your chip carrier, in our case, which is the PCB board. And then these are the phase shifters, and you can see that they kind of look messy, and you can see that there's parts that kind of look broken, and that's because they are, and I'll explain why later. And then the last picture is the actual edge couplers on the waveguide. And you can see that visually at the zoom level, they just look like little thin wires, and which they kind of are. And the light actually will propagate through this. And you would imagine having an optical fiber at the bottom here, really close to the facet of the chip, and then light just flowing from the optical fiber through the edge coupler into your nominal waveguide geometry. Okay, now I said these things are very small, and you're not going to be holding an 18.2 millimeter thing with your bare hands, right? You need to somehow package this thing. So we need a chip carrier, and this PCB board chip carrier was made by Nick Santos, who should be on the call right now. And what this helps us do is it helps us interface with 100+ electrical connections on the chip. It also helps us interface with the TEC, thermoelectric cooler. And the reason why we want a thermoelectric cooler is because we want to minimize any type of time-dependent thermal perturbations. The issue with using a thermal-based phase shifter is that if you have any unwanted thermal perturbations, that will also cause a phase shift. And with a phase-sensitive application like this, that is not desired. We also need to think about how we're going to mechanically mount this chip, because the next step is testing. And if you can't hold your chip properly and access the input port, then it's pretty much a nice coaster for all intents and purposes. So we introduce these little holes to be able to interface with common off-the-shelf optical components and parts. So the hardware in terms of a testbed. So this is what the testbed currently looks like. It's an edge coupler setup where we basically take a tapered fiber, as you can see on the bottom here, and we take this fiber and we just bring it really close to the facet of the chip that I was talking about before. To get these images, you need 2 cameras, right? So you need the side camera, which this is showing right now, and you need a top-down camera, which can also help with the lateral alignment. So with these cameras in place, you can go ahead and actually align your fiber to your edge coupler, couple light in, and then it goes through the optical circuit, and then it goes through the emitters, and the emitter will emit the light vertically up. It'll go through this microscope, and then it'll go to our near infrared camera. The reason why we have to go through a microscope is so we can actually physically see the structures, because again, they are very small. And you can see all of these gray cables coming out, these ribbon cables. Those ribbon cables actually represent us being able to control each of the 100 phase shifters that we need to control. And they feed directly into the bond pads, which will link into the phase shifters. And the other end will go into this custom circuit that we had to make to convert some of the voltage levels. And then that's controlled by some type of computer. And to get an idea of all the different parts, we won't go through all of this, but there's a lot that goes into actually testing and a lot of moving components that need to be made and integrated together. For example, creating the control for your phase, right? You need to be able to input the correct phase into these devices to get the response that you require, right? The thermal control is its own little monster that needs to be handled as well. And then all the laser and pre-optics also needs to be thought of as well. So again, we're using a 1550 because that's common telecommunications band, and that was kind of a prerequisite to the entire project. But you will want something like an optical isolator as well, because you can imagine if you bring this very close, you'll be seeing back reflections, and that could actually affect your laser. So once you have it actually on the test bed, the next step is to phase up and steer. So what do I mean by phase up? So in the GIF that I showed you, they kind of assumed that all of the static phase biases were all equal. Like there were no static phase biases amongst all the different channels. But when you're routing, you can imagine that some routes will be longer than others. And since that's after the phase shifter, you can't correct for those anymore. So you actually need to correct for them through a calibration process. You need to basically find out all the phase shifter settings such that the far field output is going to essentially look like 1 pixel at the end of it. So the way you do that is sometimes through this gradient descent optimizer. But this is all well and dandy, right? But the scope is actually big because the parameter space is extremely big. You can imagine if you were manually doing this, you would have 100 knobs, one for each channel, and then you would slightly change them. You would slightly change the knob for each of the channels one at a time and see if it made your far field better or not. And then you would decide, okay, this knob made the best change and the most amount of change that I want, I'm going to change this. Then you would repeat the process. And if you kind of do that, then if you have 100 emitters, 2 phase shifts per, like, so you have to go like front, like one way and then the opposite way to test if it makes it better. And then let's say it takes like 6 seconds to do each knob. Then that's about 1,200 seconds per iteration. Okay, let's say we get lucky and we're able to converge in 100 iterations, right? Very unlikely. Well, that's 33 hours to phase up your array. That might not look like a lot, but that's actually a lot if you are having a lot of different static phase biases that needs to be accounted for. And if there's variations between the chips that you're fabricating. Another way to get an idea of it is to kind of think about the number of permutations that you can have. So if you have a 16-bit DAC, that gives you a voltage resolution of about 2 to the 16. So then the number of permutations that you can really have with repetitions between those values is about 2 to the 16 to 2 to the 16. So those are all the possible combinations that all the phase shifters can be in. Again, very large. So you can get lucky because you don't really have to do this in a systematic way. You kind of do it in a kind of a stochastic way. So people use what's called a stochastic gradient descent. So it's a gradient descent, but instead of checking every single knob every time, you pick a random subset of those knobs. And then you change those and you go based off of that. And that's one of the algorithms that we're exploring so far. Another one is a gradient-free approach. What if you don't need to check the local gradient every single time? Right? What would that look like and how fast would that be? So right now I've just applied a particle swarm technique as well. And I'll show you a little bit of the results for that after. But there is still work being done to apply these algorithms. And they haven't really come to a substantial convergence in their optimization yet, mostly due to project delays. But we're getting there. So some preliminary results. So the first time we actually went ahead and looked at the output of the light, our first light, we saw that we had some unlit gratings. And those unlit gratings correspond to broken parts of our optical circuit. So we took it under a visual microscope and did notice, like, yes, there were some broken phase shifters. And that was actually due to a lot of, due to how the chips were being handled in a post-processing step. So after we figured that out, we got them remade, and then we can see that we have a much better yield than the first one. I think only 2 are broken here. So after getting the actual OPA working, and we can like feed light through, and we know that the actual optical circuit is working the way we want it to, we need to start applying the phasing up algorithm and the actual steering algorithm. So what you see is actually just the far field image. It was cropped and everything, and you're seeing the change in the pixel value as I apply different biases to each of the different phase shifters. It's not really coming to convergence yet. I think this image really just explores the exploration phase of the particle swarm optimizer, but you can see that we're kind of getting there. So to bring everything back, right? So we're developing an on-chip optical phased array for intersatellite links using a 100 emitter dual ring array. We developed the various optical and electronic components required to test and use said device. And then Nick has developed a chip carrier which interfaces electrically with 100+ bond pads on the photonic chip, which is really awesome. And then we created a test bed in terms of the hardware and software to fully characterize the OPA. And then the idea in the upcoming months is to fully characterize this thing in terms of the beam properties and actual steering capabilities, so that we can make a decision on the next version of the OPA that we're also making. So what is this end goal, right? What is the end goal of all of this? So we basically want to mature this technology to a level where the beam steering application can be applied for intersatellite optical communication. Why is this important? Well, it just helps satellite transfer data faster and in larger chunks than what we have commonly done. Thank you. Any questions?
All right, thank you, Akash, for the nice talk. Questions?
If no one has any questions, I'll ask the question, Akash, and I'm sure you can easily answer the question, but I was wondering if you can comment on how else microphotonics can enhance the capabilities of future space missions.
Yes, the other part of my thesis, I'm also working on an interferometric fiber optic gyroscope. So optical components have a lot of applicability to space systems because you can actually do a lot of different things with them in terms of actually making the focal point of your mission in terms of having a telescope or some type of interferometer system, or you can use it as a subset of your actual satellite as well. So for example, using an optical sensor, which is based on the Sagnac effect, to actually measure the angular velocity of how fast your satellite is spinning, for example. There's a lot of different things you can do with it in terms of the actual sensor side. You can also introduce an optical, what do you call it, a solar cell coating to help with the efficiency, for example. There's a lot of different things you can do with it. Hopefully that answers your question.
Yes.
Okay.
Stefan?
Yeah, hi, thanks. My question is about the thermal phase controller, like the concept of using heat to control the refractive index. Do you have any problems in that? Let's say you're like too warm and you want to cool it down. Do you just have to wait, or is there a cooler? Or is there problems with like, you kind of have to wait for it to uniformly heat up?
Yeah, so you can imagine that the actual cooling down process is going to affect how fast you can modulate this effect, right? So ideally, you don't just want to turn it on, but you want to turn it on to some level, right? So you need to actually sometimes wait if you want to let it go to heat it up to, let's say, 1 watt, but then you want to cool it down to 0, and so you can heat it up to 2 watts, for example. It places a limit on the actual frequency in which you can modulate this effect and therefore modulate the phase of your light. Yeah, so that's where the limit would be placed in terms of cooling. So you do have to wait, yes.
Okay, this is nowhere my field of expertise, but I think I once heard a talk about someone presented work where you can actually control the refractive index via like sound waves, like passing through sound.
Yes, I haven't personally looked into that myself, but I do believe that is an effect. It's just, it depends on the material of choice that you use. Like a lot of people do a lot of research into creating and developing materials that can be, that can cause, that allows you to actually go ahead and change the refractive index through a lot of different physical phenomena. These are just the two most popular ones.
Okay, cool, thanks.
I see Nicholas in the chat. Is Nicholas, do you want to add on to this?
No, this is just with respect to the temperature control, because this is, again, Akash and I are sort of joined at the hip at this project, along with the rest of the teams in association with Honeywell. So my focus of my research was the thermal control. So just with respect to how that system is controlled, we're investigating the performance of essentially off-the-shelf thermoelectric coolers for uniform temperature control of the entire array via the underside of the chip. In doing so, essentially setting these benchmarks, we're aiming to just reduce the crosstalk between the active phase shifters and the adjacent inactive phase shifters as much as possible. Yeah, sorry.
Okay, cool.
All right. Other questions or discussions? If not, let's thank both Peter and Akash for the really great talk. I'll clap for everyone. And that's it for this month's TEPS seminar, and our last seminar will happen next month. All right, stay safe, everyone.